Part 4 then of our look at solid code principles, and that inevitably brings us on to the letter I, which stands for the interface segregation principle. And this is normally formulated in a couple of ways. One is it says that interfaces belong to clients, not to libraries. And maybe the other way it's often formulated is that clients should not have to rely on methods that they do not use. Now, neither of those I find particularly helpful until you've understood a bit more of the nitty-gritty of it, and then they kind of make sense looking back at them. What I would normally say is the approach we should follow if we want to conform to the interface segregation principle is to say that any interfaces we write should be narrow and stable. Narrow in the sense they only have a small number of methods, and stable in that that number of methods doesn't grow as time goes by. And in fact, those two rules are essentially applications of the first two of our solid principles, the single responsibility principle and the open close principle. So the idea that an interface should be narrow is really saying what the single responsibility principle says, that an interface should only be responsible for one job. It shouldn't keep having lots of other jobs. And then the fact it shouldn't expand, the fact it should be stable, is really saying the same as the open close principle, that when we add new functionality, we do it by adding new classes, not by modifying existing classes. Well, it's slightly different because we're applying it to interfaces, but it's certainly along the same lines. Now, the example I've got to show you today is based on a thing called turtle graphics, which you may have come across. It's often used as a way of teaching programming to children, whereby you actually physically have a piece of paper that you spread out, a large piece of paper you spread out on the floor, and on that you put this very simple robot known as a turtle. And then you've got the ability to instruct the turtle to move to a certain location on the paper. And additionally, inside the turtle, you've got a pen, and that pen you can either have up or down. And so if the pen is down, when the turtle moves, it draws a line on the paper. And that way we can do all sorts of graphics and understand some of the basics of programming. So I'm not going to do this with paper on the floor, but I can do it in Windows using a WinForms application. So that's what I've got here. Let's just run it up and show you what's happening there. Then we can see we've got this WinForm, and I've got a command menu, and I've got the ability to draw 4 basic shapes, of which actually only the line is implemented at the moment. But if I click on the line, you can see the turtle there effectively drawing the line across the page. And that's all done through an interface that I've written here in Turtle Logic called iTurtle. And you can see it's nice and simple. It's got the 3 basic operations we said a turtle has. So moving the pen up and down so as to whether it's on the paper or not, and then just a move that takes us to a particular location. We've also got to have the ability to set this thing I've called an iCanvas, so that represents the paper that the turtle is actually going to draw upon. And so we can see in our form what's happened here is in the initialize, we receive this turtle, we set the canvas to ourselves, and then in the draw line that we've got there, we simply lift the pen up, then we move to a location, put the pen down, move to another location, and that's going to draw the line as we've seen it. The implementation of our turtle is in here, and there you can see we've got our up and our down. We simply set our canvas, and then we've also got our move. The only slight complexity here, which isn't really relevant to what we're doing, it just makes the application look a bit more realistic, is that when we move, if we're actually drawing, we do this staggered draw, and the staggered draw breaks the draw down into a number of steps that we can see are done like that, with a slight delay between each one, and that's what allows us to mimic the behaviour of the turtle. Obviously, it would be very simple to write this so that the line just appeared there, but we've got it so the line builds up gradually. But the key thing is, if we look at this turtle interface, it's already obeying the interface segregation principle in that it is narrow, it focuses on a particular job, and we shouldn't really think we have much need to expand that to add new methods in there. But having said that, it's also not a particularly useful interface, because we've seen all we can do is move the pen up and down and move the position of the turtle. And we also saw what we want to be able to do is draw things like lines and squares and circles and triangles. And if we had to do all that simply by calling that low-level interface, it would be possible, but it would be a bit dull. So something you might want to do is in here, we might want to, on our turtle, actually add the ability to draw, let's say, a square. That was one of the things we had listed there. So I need to put in a public async task square, and on our square we'll take a double that we'll call side to represent the length of the side. And then the first thing we're going to do is we're simply going to lift the pen up so that we're not drawing. Then we're going to move to the start point. Remember, all of this has got to be asynchronous, so I've got to put the await in here. So we're going to move, and our start point is going to be 0.5 minus side over 2 as an x, and 0.5 minus side over 2 for y. So this works on a 1-by-1 coordinate system, so we're going to be offsetting from the center there. We're then going to have to put the pen down to start drawing, and we're going to move from the start point. So let's now move downwards. So if we go to the y value of plus side on 2, that'll draw us down. Then if we move again to both of them being plus, then that will move us across the bottom. Then if we move to x being plus and the y being minus, that will move us up the right hand side. And then finally, if we move back to where we started, then that will complete the square for us. So we've put that in there as a new method on our turtle, which is not an unreasonable thing to do. But the thing we then should not do, if we want to make this conform with the interface segregation principle, is simply dive in there and add onto our interface a method called draw square that we've already got the implementation for, because that would break this idea that clients shouldn't be given methods they are not interested in. Our current client, the turtle form, has no interest in drawing squares that we know of, and so if we just put that function in there, it would start making this interface more complicated than it needs to be. It would have methods that our turtle form wasn't necessarily interested in. So instead of changing that interface, one simple way that we can implement the interface segregation principle is to use interface inheritance. So what I'll actually do is in here, I'll add a new interface, and I'll call this shape drawer. And then on this one, I will derive this from turtle. So that will pick up the up and the down, the move and so forth. I'll put into that my task square, which takes double side. And then all I need to do in my turtle itself, rather than implementing turtle, if we implement shape drawer, then that now is implemented by that square function we already had. So it's a bit of an odd way around to do it. But the key thing is, all of those changes we made to the library did not have any impact whatsoever on the existing client, our turtle form, because we didn't modify the iTurtle interface. We created a new interface, and so we don't need to make any changes at all to our turtle form. Obviously, it still can't draw a square, but it's not broken in the sense it can still draw a line in the same way. And then as time goes by, if the client wants to start making use of the new features, it's up to them to upgrade to that. So if we go into our turtle form now, I can, as and when I choose, change that to a shape drawer, and also need to change it up there. And so now we're dependent on the new interface and we can make use of it. So here I've just got an empty method already for drawing a square. So if I say await and then underscore turtle dot square and give that 0.3 as the side length. And so now when I click square, we can see it draws the square in the way that we wanted. So that's the idea we said, that it's the client that owns the interface, not the library that owns the interface. Just because I had a new feature in my library, I didn't force that upon existing clients by putting a new method in the interface. The interface should be designed to fulfill the client's needs, not simply to expose all of the functionality that we have in the library. And so doing it that way meant clients, as they feel like it, if they need to draw a square, can upgrade to the new interface. That said, we still have a bit of a problem because our eye shape drawer is now drawing a square, but clearly that's insufficient. There are going to be more shapes you want to draw. But if we now put another method in there for circle and we put another method in for triangle, then with each one of those, we're once again breaching the interface segregation principle because it's an unstable interface. It's growing every time we think of a new shape, and essentially that is going to be an open-ended problem. So actually we can do something rather clever here. And once again, as we saw with the open-close principle, we can rely on the strategy design pattern and actually make a hugely flexible interface for this shape drawer, which will mean that it never needs to change again. And the way I'm going to do that is this. I'm going to pop in another interface. So we're getting a lot of interfaces in here, but they all have jobs to do. And this one I will simply call eye shape. And we'll make that public. And for now, we won't give that any methods. We'll see what they need to be as we come to it. But now I'm going to change the shape drawer. So I'm going to admit that was a mistake. A shape drawer shouldn't be specifically drawing a square. And instead, it's simply going to have a single method called draw shape, which will take as a parameter one of these shapes from the interface. And I think, although the details will come, you can already see where we're going. Now that we've got this interface eye shape, then all we need to do is write a square for drawing a square, a circle for drawing a circle, triangle for drawing a triangle, and then we can pass each of those as a strategy effectively into our draw shape. But the eye shape drawer itself is now completely stable. What other method could an eye shape drawer need other than the ability to draw a shape? So what we now need to do, obviously, is change our turtle so it implements the new eye shape drawer. So we'll just do the implement interface. And so now we've got the draw shape. We're going to need to make that async. And what it's going to do is it's going to call a method that we haven't even yet put in there, but we're going to do shape.draw, passing in our self as the thing we're going to draw with. And that we're going to make an await so that we get that staggered drawing. And so now let's go back to our interface. So on here, we will put task, draw, and that one is going to take an eye turtle as the turtle we're going to use to do the drawing. So that now should be happy. And then we can do something like add a square on there. So if I now add a class, call this square, and then we need to get square to implement eye shape. That then needs to have the method draw. And then we've already got the code for that, so let's just nick that out of turtle. So we'll take that. We're not going to have a square method on turtle at all anymore. We'll put it in here. And then the only thing I've got to bear in mind is all those methods that were previously the turtle was calling on itself, we're now going to have to call them on the turtle that's passed in. So if we do that, and that, and that, and that. And then the other thing we can see is we don't know what side is. So that's something that I would suggest is best passed in as a constructor parameter. So if we put a constructor in there, then there we can put the double side. Then we'll have a private member called side, initialize that there. And then in here, just a load of places. We've got to change that. And so that should now all be perfectly happy. And then if we go back to our form, That's obviously complaining because Turtle doesn't have a square method anymore, but we can now just change that to draw shape and then new square, and then we pass in that 0.3 as a parameter. And if we run that, then we can now see the squares working just in the same way that it did before. And now we can go on to implement our circle and our triangle without changing any interfaces whatsoever, following entirely the open-close principle and more specifically the interface segregation principle. So if I just add a new shape, so let's add a new class called triangle. And then rather than implementing that, I've actually prepared the code earlier. So here we've got the code for a triangle. And just pop that in there. And similarly, we can do a circle. You'll notice I'm adding these classes into the Turtle library, but actually one of the benefits of doing it this way is they could go anywhere. They don't need to be in the same library, and so once the Turtle library has been written, is sealed, is finished, then we could be putting these into the client code or in some other shape library that we provide. Really doesn't matter at all. Let's just take our circle from there. Just need to add a namespace in each of those. So put that in there and in there. And then finally, if we go back to our form and where we've left the blanks, so simple. I can, on the circle, do a draw shape, pass in a circle and leave 0.3 as the radius. And then we could also, in here, pass in a triangle. The triangle has a base length, but again, let's leave that as 0.3. And so now we can see that if we run that up, we've got our square that we had before, but now if I draw a circle, we get the circle around there, and if I draw a triangle, we get the triangle fitting inside the square like that. So that was using the strategy pattern in a rather similar way to what we did earlier to help us with the open-close principle, this time to help us with the interface segregation principle. So our interface now is just so simple, it's never going to need to extend, and we extend it by adding new classes, squares, triangles, circles, whatever they may be. But that's now going to be a very narrow, very stable interface that we can hand over to anybody. That said, actually, that shape drawer probably is still breaching the interface segregation principle because of the way that we've done this inheritance. Because shape drawer is derived from iTurtle, therefore actually shape drawer has, as well as the draw shape, it has canvas and move and down and up. And though we've seen that our implementations for square and circle and so forth do use those methods, they're not necessary in the interface itself. There's nothing fundamental that says if you want to draw shapes, you need to have an up, a down and a move method. You should just have that draw shape. So iShapeDrawer is a little bit wide, and what we should really be doing is separating these two out completely. Now that said, there is one thing in iTurtle that iShapeDrawer does require, I would say, and that is a canvas. You can't do a shape drawer without having something to draw upon. So what we'll actually do is a restructuring, and this one may remind you a little bit of what we did in the video on the Liskov substitution principle, because you can see how these are all interrelated. So I'm going to add another interface, and this one I'm simply going to call iDrawer. And the only thing that we have to have in a drawer interface is it's got to have the ability to take a canvas. So let's take that from our iTurtle, put that into our iDrawer. And then we can say that our shape drawer now simply derives from iDrawer. So it's got to have a canvas, but there's no requirement for it to have a move or an up and a down. And our iTurtle also has to have a canvas, so we'll put that in there. And then if we go to our turtle itself, then that's going to be both an iShapeDrawer and an iTurtle. And you'll see already that implements all those methods necessary from those interfaces. Now, if you take a look at where the turtle is now, you might think that the turtle class itself is starting to get a bit busy. It may be starting to breach the single responsibility principle because it's got quite a lot of methods doing different things. And that may well be true, but it's not what we're focusing on at the moment. So although there's room for improvement here, the important thing is we have got our interfaces right. And in a sense, they're more important because our interfaces are what's going to be seen in the outside world, whereas our implementations, if we later on want to fix them, make them more structured, it doesn't matter as long as the interfaces are right for everyone who's using them. So now all we need to do to get that to work, if we just take a look at what's happening in our turtle form, we can see we've got a slight error in that we now don't have the basic turtle graphics in there because, remember, our shape drawer is now, we've called it a turtle, it's not, strictly speaking, a turtle because it doesn't implement iTurtle. So this is one of these cases where we could have used both interfaces, but actually it would make more sense here, I think, to actually have another one of these shapes for drawing a line. So last thing we can do here is go for a new class. We'll call this line and implement iShape. And then just take that code, pop that in there. And now we can, in here, do the same as we've done in all the other ones. So we just await turtle, draw shape, and in this case a line, and I haven't bothered with any constructor parameters on there. And everything should be happy, so we can draw a line, we can draw our square, we can draw our circle, we can draw our triangle, and we can draw any other shape we can ever think of. And when we do that, it'll be entirely in accordance with the open-close principle, so adding a new shape is adding a new class, not modifying existing classes, but that's achieved because we've obeyed the interface segregation principle. So our key interfaces are iDrawer, simply says, if you're going to be a drawer, you just have to accept a canvas to draw upon. We've then got iTurtle, which says if you're going to be a turtle, you've got to have the up, down, and move methods. And then we've got the shape drawer, which says if you're going to be a shape drawer, obviously like a turtle, you've got to be a drawer, but then you've just got to have that draw shape method. Those are all implemented in the turtle, but that's another matter. The important thing is we have got narrow and therefore stable interfaces that we are presenting to our client in the turtle form. Once again, as I mentioned when we were looking at the Liskov substitution principle, actually the final one of our solid principles, the dependency inversion principle, is one that's going to tie this all together, because at the moment we haven't really looked at how we hook all these interfaces together. I've kind of hidden it there. If we look at our turtle form and look at the constructor for that, you can see that it's taking in this interface iShape drawer, and it's actually down here in my program that's simply been hard coded. And a lot of what we're trying to do here is avoid that sort of hard coding. And so that's what we'll see next time when we look at the last of the 5 solid code principles, the dependency inversion principle. But until then, hope you enjoyed this video. Do subscribe if you want to see more videos, and also any questions or comments, pop them in the comments section below. And thank you very much.